Section 3.6 Symmetry Adapted Linear Combinations. So remember, molecular orbitals are linear combinations of atomic orbitals. And the most commonly used MO theory is symmetry adapted molecular orbital theory. So let's look at a few examples. So over here, this s orbital and this orbital, they can overlap and form a sigma bond only because they have the same symmetry along this molecular axis. Same here, if you look at the symmetry along this axis, this s orbital is symmetric and this pz orbital is also symmetric, and therefore they can overlap and form a sigma bond. Now let's again look at a s orbital and a p orbital, but this time along this molecular axis. You can see if you rotate this one 180 degrees, no problem, symmetric. If you rotate this one 180 degrees, well, you change the sign of this px, and therefore these two orbitals, their symmetries do not match. They cannot form a bond. Let's imagine this is BH3 with a D3H point group, and then it's possible for the three hydrogen atoms to interact with each other. So let's ignore whatever this atom, it can be boron here, but ignore this. So if you have three hydrogen atoms this way, they can interact with each other in a constructive manner. That's A1 symmetry. This is symmetric with respect to rotation or mirror planes. And then remember, if you have three AOs, three 1s orbitals from three different hydrogen atoms, you can make three MOs. So what are the other two MOs? One here, another one here. So these two MOs have higher energy, and you can immediately tell this one has one nodal plane here, this guy has one nodal plane here. With more nodal planes, the MO has higher energy. And then now let's look at this situation. These two actually belong to the E group. They are degenerate in the D3H character table. Okay, now I want you to kind of imagine this is now not BH3. This is just ammonia, all right? So this dot is above the plane. So this dot is nitrogen above them. Fine, we can do just similar analysis. Again, this is just A1 in the C3V point group. And this is the E symmetry with a degeneracy of 2. Again, you just need to imagine this nitrogen is above the plane. Finally, how about just 3 hydrogen atoms? If you put 3 hydrogen atoms this way, well, same analysis. Now finally, H3 plus. Let's say you have H3 plus with one positive charge. You have only 2 electrons. All right, and then what about the MOs of this H3 plus? Again, 3 MOs because each hydrogen still contribute one 1s orbital, so 3 MOs. And the 2 electrons, there are only 2 electrons, will occupy this MO. This 2 will be unoccupied. Actually, in this case, you may view H3 plus as a aromatic molecule. Again, aromatic molecule. Again, this is constructive interference, and there's no electrons in this orbital or in this orbital. So both electrons occupy the lowest energy orbital. It's very stable.